Okay, so dear participants, a very good evening and welcome to the third session of the day. We are here with Dr. Satyajit Mohanty. He is currently working as an associate professor in the Department of Electrical and Electronics Engineering, VIT Vellore, Tamil Nadu. He completed his PhD from the Department of Electrical Engineering, NIT Rourkela, in the year 2017. He has published paper in reputed journals like IEEE Transactions on Sustainable Energy and IEEE Transactions on Energy Conversions. He has completed his master's in the year 2012 from SOA University in the specialization of power electronics and drives. He has more than 10 years of experience in both teaching and research. He is also a reviewer of reputed journals like IEEE and IET, etc. He is a member of Indian Society of Systems for Science and Engineering, a Bhubaneswar chapter. His research area includes solar photovoltaic systems and microgrid. So I welcome the speaker, and now I will hand over the session to Professor Satyajit Mohanty. So please.
Thank you very much, Shibam sir, for welcoming me. Thank you, Chiru sir.
Yes, sir.
So I will be sharing my screen. Is my screen visible now?
Yes, sir.
And my PPT?
Yeah, it is in normal mode. Make it full screen, sir. Slideshow. Yes. Okay, now.
So very good evening to one and all. So today I'll be delivering my talk for 1 hour. So which will be more focused on the maximum power extraction algorithms for a standalone and grid connected photovoltaic system. Okay. So which is a part of a DC microgrid. So we all know that DC microgrid is a very huge area in which we get to work in different modes like decentralized, centralized, and distributed. So among this, I will be focusing on the DC-DC converter part. Okay, so how to extract maximum possible power from the solar photovoltaics. Okay, in any scenarios. Any scenarios means maybe uniform insulation or non-uniform insulation. So these are my contents I will be covering. So I will be basically showing the experimental setup in which you can perform the experiments, and I will be discussing the modeling part, how to model different PV cells so that you can extract, you'll be able to extracting maximum fill factor, and you will be able to extract maximum possible power from it. And I will be discussing some of the MPPT techniques, which do works in either in the shading conditions or in the uniform insolation levels. So coming to the basics parts, we know that in this current era, in this world of heightened tempo, we need to look for replacements for the fossil fuels. So the best replacement is the renewable energy. We have numerous renewable energy sources like solar, wind fuel cells. So among this, the solar is found to be more promising as compared to the rest renewable energy sources, which can be used in different modes like standalone systems, grid connected systems, and distributed power generation systems. So these are the clear view in which you can have a clear, we all know that these are the renewable sources and these are the non-renewable sources. So the first PV cell was invented in the Bell Laboratories in 1954. So this is the first PV cell that is invented in the left hand side see, and right hand side is the application part. So a solar panel has been mounted on the tower to extract maximum possible power. So this is the general form of a photovoltaic cell. We need a photovoltaic cell, we can say it is nothing but a large diode. Okay. So whenever light strikes the surface of the panel, so the electrons gets excited and it moves through the load, okay, through the N and the P substrate. Okay. So these are the two filaments which has been connected, which has been sandwiched one upon another. Okay, so and a load is connected. Whenever the sunlight or insolation from the sun strikes to the surface, it generates electricity.
Excuse me, sir.
Yes,
Sir, can you please hide that bar which is showing you are sharing? Hide that. Yes. Yeah. Thank you.
fine, fine. Okay. So if we connect different, we know PV cell is of ample amount of voltage like 0.5 or 0.6. If we connect it in series parallel, it forms a module. And if we connect numerous PV modules in series parallel, it forms a PV array. Okay. So depending upon the aspect, whatever we need to connect the cells in series parallel. And this is the general, when we go for modeling for a solar PV cell or for solar PV panel, we need to model it. Either we can model for a single diode or we can go for a two diode. So single diode is always chosen over two diode because here the parameters are less. Okay, here we can easily form a photovoltaic panel. But if we go for two diode, the complexity increases. So therefore, we normally go for a single diode PV model. And these are the equations, the main equations. You can see how to find the photovoltaic current, that is the output current. Okay, you can see over here, this is the IPV, and this is the diode current, and this is the photogenerated current. So this is fully depends on the temperature and the insolation. So these solar photovoltaic systems, it totally depends on the insolation and the temperature. So whenever there is high amount of insolation, so we obtain high current because insolation is directly proportional to the current. And when there is an increase in temperature, there is a slight deviation in the voltage. So this is a system. So first I'm showing for a standalone system. You can see a PV module is there, which is connected to a DC-DC converter followed by a load. So depending on your application, you can connect a DC-DC converter as an intermediate in between the source and the load. It can be a buck if you have a low power application. If you have high power application, you need to have a boost converter. And if you need to charge a battery, okay, so charging and discharging will be going on. In that case, we can use a buck boost converter. So we know in a DC-DC converter, we have a switch. We need to generate a pulse width modulation for the switch. So for that, we need a MPPT controller. And because we know the photovoltaic panel is highly volatile in nature, it totally depends on insolation. So insolation is very much volatile. Okay, so we need to take care of the fill factor. So fill factor means the maximum power which can be generated divided by to the maximum available power. Okay, so we need to extract the maximum fill factor. So you can see, so the main aim for is to propose a DC-DC, or you should propose a MPPT controller. Okay, it should be a meta-heuristic, it should be adaptive, and it should be so efficient that it can be able to tackle any change in insolation patterns. Okay, so more clearly, more depth we will go in the next slides. So you see, so this is the output waveform of a photovoltaic panel. So you can see this condition only this condition arises whenever you have a constant uniform insolation. Suppose we have a standard test conditions that is known as STC, in which we have 1000 watt per meter square and 25 degrees Celsius. Okay, so this is the standard. If we take that, we will obtain this response. So you can see this curve indicates the power versus voltage curve, in which we have a local peak, or you can say a single peak, okay, which is very easy to extract this power by using any type of conventional MPPT. And the other curve is the current versus the voltage. Okay, so ISC is the short circuit current, which is the maximum available power, and VOC is the open circuit voltage, is the maximum voltage available. So our objective will be extract this VM and IM. So VM into IM is nothing but the PM. So that is the maximum possible power which can be generated by a photovoltaic system. So for generating this, we need to have a DC-DC converter. In absence of DC-DC converter, extracting maximum possible power, we can say it's never possible. So normally in such scenario, the cloud plays a great role. Okay, it has a great role in generation in creating disturbance in the process of generating maximum power. Okay, so these are the scenarios we can may arise. So like we can say, so regularly we need to clean the panels. Okay, regularly means you can say 15 days, 1 month, you can use some liquids to clean it, so that the dust which is gathered over here, that will be eliminated, and we can generate maximum possible power. Maybe some trees, the shades, you can see the shading pattern is, so this part is be acting as a load, because these others are known as healthy panels, and the part which is shaded, those are known as the unhealthy panels. Okay, so anything which comes in between the insulation and the photovoltaic panels, okay, it creates a disturbance in the process of generating maximum power. So we need to develop such algorithms so that we can handle such scenarios, and we will also be able to extract maximum possible power. Either it may be a standalone system or it may be a grid connected system. So now, so earlier I have depicted one IV and PV curve in which we got a single peak. But here the scenario arises of case of a multiple peaks. So here the first curve shows the current versus voltage curve under changing insulation patterns, or you can say partial shading conditions. So such pattern, the first curve, the first such pattern is known as a staircase pattern, in which we have multiple peaks. Multiple peaks consist of, you can see, numerous local peaks and a single global peak. Okay. In the second diagram, you can see the curve between power and voltage, in which we have 3 local peaks and 1 global peak. And the most challenge over here is that to implement any technique which will able to distinguish between the local peaks and it will go to the global peak. What happens in conventional MPPT? The MPPT, whenever it, suppose the first case is this is 100 watt. So if you implement the conventional MPPT, so it will oscillate over here. It won't differentiate that it has more maximum power available. So this is the most, we can say the most drawback of conventional MPPT algorithms. So in such scenario, we need to develop adaptive algorithms. We need to check some conditions, that is it the true power which we are really want to track, okay, or it's a false local peak. So that way we need to develop algorithms. And this is one of the, we can say, the shortcomings of solar panels. So what happens, I have depicted about the shading patterns, okay, which part of the solar panel is shaded by some clouds or maybe any intermittent. So that portion will act as a load instead of a generator. So we normally connect it in series so that high amount of current can flow, and a series set will be connected to another series set so that more amount of current we can it able to generate. But if a particular cell is shaded for a long amount of time, okay, so what will happen, instead of generator it will act as a load, which will result in a crack in a photovoltaic panel, resulting in a hotspot condition. Okay, so this is the most drawback of a solar panel, and at the end it will get damaged, it may burn, resulting in losses in the form of heat. So therefore this is I have taken a photo in which we did experiments, and that resulted in this such panels. So forcefully we created such scenario to create a hotspot in a PV module. So how to overcome such hotspot scenarios? So for overcoming such scenarios, we need to connect diodes. So the diodes which are connected in parallel to the photovoltaic module is known as bypass diode. And if we connect diode in between two groups of PV modules, that is known as blocking diode. So what they do, suppose we have a panel. So this is the panel 1. Okay. Due to some conditions, it is receiving non-uniform insolation levels, and rest 3 panels are the healthy ones. So this first will act as a load instead of a generator. So at that moment, the diode will come into act, okay, and it will bypass the current from the healthy panel to the external load circuit. Similarly, the blocking diode also plays the same role. If a group of panels is acting as a load instead of generator, the blocking diode will bypass the current, okay, from the healthy cells. The current won't flow through the unhealthy one because it is acts as a load, and it will go to the external electric circuit. So I have done various literature surveys. So few papers I can discuss that for uniform insulation labels, we have the most promising is the Potter and Observe incremental conductance. So these two are the most promising. Apart from it, we have like open circuit voltage techniques, short circuit current techniques, and many more. Okay. Then when we come to non-uniform insulation levels, in this we can implement meta-heuristic algorithms, techniques like flashing firefly, like Gray-Wolf optimization, modified particle swarm optimization. So they are adaptive techniques. So when the hotspot condition arises due to the partial shading conditions, so such MPPT, the maximum power techniques, will be able to tackle such scenarios and will be able to generate maximum possible power from the source. So these are some of the reviews. I won't go into it. So first of all, I will show one of the experimental setup which we use for generating maximum possible power. It may be for uniform or from a non-uniform. Okay. So in this, the objective of this part will be, we will be using Agilent simulator. Okay. So what is Agilent simulator? So it's, you can say it's a replica of a real-time simulator. Instead of a solar panel, so if you use solar panels, you need to wait for the insolation for performing the experiment. Okay. But if you use Agilent simulator, okay, so it's like a human, you can replica of a real-time solar panel. So even if it does not require insolation to work, it can work in any weather conditions. Okay. It has the potential to generate insolation levels of its own. So these are the systems which we developed and we worked. Okay. So you can see we have a dedicated E4360A Agilent simulator. So this is the simulator which we worked. So this simulator, actually this company is now currently known as Keysight Solutions. Earlier it was known as Agilent simulator. It has only one model, E4360A, and it has the ability to produce 1.2 kilowatt. Okay. So 1.2 kilowatt system we can maximum produce. Okay. So it has 2 racks in the back side. Each rack is of 600 watt. Okay. So you can tell the seller that I need 1.2 kilowatt or 600 kilowatts. So accordingly, the person will implant and send it to you. Okay. And we have a control system in the back side. Okay. So this Agilent simulator, for to see it's working, we also need a desktop. You can see. So this is the output. You can see the things which I showed. These are the hardware applications of those. In the bottom, you can see these are the VMP, IMP, VOC, ISC, everything. You can see my cursor over here. So it's clearly displayed over here. And these are the patterns. So this is the P V curve, and the above is the IV curve, which is reflecting multiple peaks. So this currently this experiment has been carried out for a partial shading conditions. Okay. And the controller used is DSpace1104. So this is the system for the controller. We have Hall sensors for measuring the voltage and current. We have DC-DC boost converters. We have a load, and we have a DSO, digital storage oscilloscope, to see the output waveform, to see the tracking waveform. So I will be showing the response of this. So this is the total hardware part which we used. Okay, for generating directly in any time you can do the perform the experiment and obtain the output. And the second can comes when you work in real time. Okay, so these are the things which I said. Okay, so it has actually two modes. One is we can say table mode and another is normal mode. Okay, so normal mode means it can act as a normal battery also. If you don't want the behavior of a solar, because we know solar the output is DC, we simply it can work as a DC battery. Okay, you can make it work as a DC battery. So these are the view of agilent simulator. So I took this so that I can show you. So this is the rear view and the above is the front view. Okay, and the display is the VOC and the ISC. You can see it's the 50 volt it's showing and ISC is 4.004 ampere. And this is the back side. So you can use any of these connectors. You can use LAN, USB or GPIB, okay, connectors for using this agilent simulator along, and it will be mounted on the your you will be mounting the software on your desktop. So in the back side there are two racks. Each rack is of 600 watt, and another is a power supply unit, which is a mandatory. So this is the fixed mode which I was talking about. You can see. So this behavior is normal like a battery. We need a constant voltage, constant. Okay, so constant voltage can be easily we can produce in the fixed mode. Then this is the simulator mode. Simulator mode means the mode in which we have a single peak. Okay, single peak, or you can say single global peak. So that scenario, this scenario arises only in the case of uniform insolation levels, in which it's reflecting only one and only one peak. Okay, so for plotting this graph, we can have maximum of 4096 okay point tables. So same 4.4096 point tables points can be obtained in this simulator mode as well as in the table mode. So the third one is the table mode, which I have used for performing the experiment for non-uniform insolation levels. So you can see here, here also we have 4096 point tables. So tables, the mode is it's a non-volatile. You can store it and you can use it for your future use. And these are the about the D space, sensors, and the design converter ratings. Then, if you need to work in get an exposure in real time photovoltaics, so you can see I have got this glass from IIT Bombay for performing the experiment. You can see the glasses which are laid upon the panel. So each glass have a rating. Okay, some glasses are of 1000, some are of 1800. So the opacity increases. Okay, the opaque increases of each. It's a calculated value when you brought it for experiment. Suppose you can see one is the clear glass, which is the topmost. It allows to pass maximum insulation. After that, the second one connected to it, it will block little bit. Okay, accordingly. So you can see different types of intermittents are used so that it should not, the insulation cannot fully strike the surface of the panel. Okay, and above it, for measuring the insulation, we have a device we can see here. It's known as a pyranometer. Okay, this pyranometer, what it does, it measures the insulation coming from the sun. And for that, we have also a setup, that data logger and modem, that we can have a watch over the 24-hour scenario. Okay, that what is the insulation for the day or for a month. Everything is stored in the data logger and modem. Okay, so same system used, only the difference is that here we have used a real-time solar panel instead of a agilent simulator. So these systems can be used for verifying your MPPT algorithms. Same thing, we also in the laboratory, that picture I haven't given, we also have a grid connected systems. Some students also work on it, grid connected systems. So in that case, we need to have a power balance between the DC-DC converters, a synchronism between the inverter and the grid. So that you need to take care, which is the most challenging part. So next, so this part will be, I think, very interesting. So when I did some research work in this photovoltaic, I thought that to model PV panels, okay, mathematically, okay, for that I developed one of the patterns which I suggested, which I proposed, okay, and I have compared with the former or the conventional patterns which are available, and I found that my pattern is more promising, is more efficient, is having high fill factor as compared to the conventional ones. Okay, so you can see, so we can have a set of modules or panels with bypass diodes or without bypass diodes. So these are the two strategies, and these two strategies can be implemented in these conventional techniques like series parallel, TCT. TCT is the total cross tied, then bridge link, then followed by it I have proposed a technique that is the ring pattern. Okay, so what is all this? We will go more depth into it. Okay, so these are some of the configurations. What you need to do, you need to form some configurations, and you have to examine it in the practical, in the experimental setup. You have to find the fill factor. You have to find the efficiency. Then you can say that which type of topology is better as compared to the conventional one. So all these algorithms have gone through that experimental experiments, okay, and the data is available with me that I will show in the next slides. So this is the scenario. So once again, I am showing you this is a scenario which happens. Okay, so these are the partial setting modules, and the white one is the healthy cells. Okay, healthy modules. So whatever I said, you can see. So this red color diode, the red color indicates that the diode has activated, and the other black color diodes are not activated because these are connected to the modules which are healthy and they are receiving uniform insulation levels. So these are the responses which I already discussed and also shown experimentally. Okay. Now, so this we can see in the first few slides, I discussed about the single diode model. So you can see I have connected 3 different single diode models in series. Okay, so 3 sets of diode modules having different insulation levels have been connected, G1, G2, G3. Okay, so these are the these are the functions. Okay, for 3 modules, and the 4th one is the voltage, and these are the whole total equation. Okay. So this is the calculated value for a bypass diode. Okay, 10.6 ohm if the VD is less than, if the diffusion drift voltage is less than equal to 0, and 0.1 ohm if it is greater than 0. So I will come to the main part. So these are the you can see that only difference is that here we don't have a bypass diode in the output. Okay, so 2 configurations can be found either with bypass diode or without the bypass diode. So these are the IV curves equations, okay, for the saddle, for the unsaddled group of cells. Okay, so this is the thing which I wanted to demonstrate. So first one you see there is the SP configuration, that is the series parallel configuration. So what happens here? What is done? This is the conventional one. Okay, in this we can have you can see 5 cells or 5 modules are connected in series, and 4 set of 5 modules are connected in parallel. Okay, so in this what we take into account, okay, so IN, Vj and lambda j. Okay, what is the lambda? Lambda is the number of the modules. Okay, so here we have taken 20 cells, so you can see here it is the 20 cells. Okay, so n is equal to 1 for m1 to m5, 2 for m6 to m10, 3 m11 to m15, and n equal to 4 for m16 m20. Okay, so because n is current, for the current, so I equal to I1 plus I2 plus I3 plus I4. and across it the voltage is J equal to 1 to 5. So all these set of modules are parallel to each other, the four sets. So it's having BP voltage. Okay. So this is the series parallel configuration. Then comes, this is TCT configuration. This is known as total cross tied configuration. So what happens? So in that, the difference you can clearly observe that the middle part has been connected. The M1, M6, M11, M16 is connected. Similarly, this M2, M7, M12, M17 is connected. Okay, so such pattern is known as total cross ties. Okay, and these are the mathematics behind it. So these are only the representations of current and voltage. My aim is to only I have depicted here the current and voltage. Then this is BL. BL is not as bridge linked. Okay, this is one type of configuration. It's bridge linked. So the pattern, you can remember those patterns. Such patterns, if you find in any systems of solar panel, so those are known as bridge linked. Then coming to the proposed RP configuration. The RP is known as the ring pattern configuration. So after rigorous topologies, doing different experiments, I found that this RP configuration is somehow better than the conventional configurations. Okay. So similarly, these are some are the currents. There are 27 unknowns, which comprises of 8 module currents and 19 module voltages. Okay. So now what I did, I took the same systems. Okay, I took the series parallel, I took the total cross tied, I took the bridge linked, and finally I took the proposed RP. So these configurations were exposed to do real-time photovoltaic scenarios. Okay, and now I will show its performance. So this is the system which I used. Okay, so only for the study analysis. So it involves the only Agilent simulator and the system connected to it. So all these systems one by one I dumped into it. Okay. So you see this first. So here the global peak I obtained is 50.227 in case of series parallel configuration. Okay. So it gives a very clear-cut idea if you use this system for photovoltaics. So BMPP is 83.993, IMPP is 0.59. If you multiply, it will come around BMPP, IMPP. Okay, so this is connected to the MPPT. So okay, so our focus will be on this 50.227 watt, and the fill factor is 0.473. Okay, so you can see the model, the mode is table, and the name is SP given over here, series parallel. Then big B is TCT. In TCT, I obtained 51.077 watt. In that, I have BMPP of 83.3 and 0.613, and the fill factor is 0.403. So in between these two, I can say that, excuse me, that TCT is having more global power or maximum power as compared to series parallel, but the fill factor of series parallel is somehow better than the TCT. Then coming to the bridge link. Okay, in bridge link we are obtaining the power of 50.232 and having a fill factor of 0.39. So this system is so reliable that we can see the fill factor directly. Okay, fill factor is nothing but BMP into IMP upon VOC by ISC. Okay, it range value rise between 0 and 1. And the last one is the proposed RP, in which you got a fill factor of 0.474 and global peak of 50.25 watt. Okay, so now coming to the comparison table, so you can see I have highlighted over here. Okay, so if you compare the maximum power obtained and fill factor, okay, so only the total cross tied is able to generate more power as compared to proposed. But from other series parallel and bridge link, the proposed RP shows the better performance. Then coming to the fill factor side, the proposed RP is better than the conventional configurations. Okay, so after forming different topologies, so proposed RP is better than the conventional configurations. So I have used this proposed this ring pattern for the photovoltaic systems, which I did for the experimental purpose. So this is the summary. So the first part is that what I discussed is that I have shown the experimental environment which we use for performing the MPPTs. Then I have depicted the different configuration strategies which are available, and I gave a comparison. So which pattern to be used so that it will be able to generate maximum possible power. Okay. So one more thing I will discuss. I will discuss one MPPT technique which I used for the partial setting conditions. I will be discussing its output, how it is done, how it is performed with the relevant experiments results. Okay. So directly I will come to the pattern, the optimization technique. So this is the gray wolf optimization which I used for extracting maximum possible power. So we have alpha, beta, delta, omega. So these are the 4 different types of wolf. So amongst this, alpha is the better one. Okay, it is followed by the beta and delta. Okay, and the rest over who is left in the pack is known as omega. So we can say alpha is the leader. So this is how the hunting behavior of the gray wolf. Okay, so from A to C they chase and track. In the pattern D they are encircling in the prey, and finally in E they are attacking the prey. So same behavior we are using, okay, for tracking the global peak in case of a partial sending conditions. Okay, so these are the equations involved in it. So first I will tell the what led to choosing this gray wolf. So in case of if you use particle swarm, we have over there 6 parameters which you need to tune. But in gray wolf only we have only one parameter, that is A. Okay. So this is A. This is the only thing we need to tune. Okay. And it linearly decreases from 2 to 0. So this is the equation which I converted for generating the duty cycle. Either you can generate direct duty cycle, or you can generate you can have a voltage control device. Okay, you can have a summing point. You can subtract the actual minus the desired, or desired minus actual, and you have to pass it. So what I did, instead of the 2-stage conversion, I opted for a single stage conversion, and this is the fitness function. Okay, so this is the system which I used. So you can see here it is not a voltage dependent. So what I did directly, I implemented the meta heuristic technique, the MPPT controller connected to a driver circuit, which is responsible for the generation of the PWM signal. And this is the flow chart of the proposed algorithm. Okay. So first of all, you have to sense it, you have to compare it. Okay. If the required power is higher, then you have to update it. Then if you have to check for the global max, if the global peak is greater than local peak, then you have to go ahead, otherwise the loop will be repeated, and you have to update it unless and until you reach the global peak, convergence won't be achieved. Okay, so you have to wait for the convergence. So this is the system. You can clearly see what I did over here is that I took rapidly changing insulation patterns. So normally people take uniform, non-uniform insul patterns. So what I did, the same system, you can see the cursor. So it's 0.45, it's 0.45, it's 0.4. In certain span of time, this 0.4 changed to 0.8. Okay, and rest modules remains the same. So this same module, okay, this pattern both are same. So for a certain time, this 0.4 changes to 0.8. Okay. So the curve is plotted in power and voltage. Okay. The blue color is the pattern 1 and the red color is the pattern 2. So for a time gap, okay, suppose this system runs for 1 minute. For the next 1 minute, this second system will run. So the transition which is found is from 0.4 to 0.8. So under such scenario, the MPPT should be able to track the maximum possible power. Okay. So this such configurations as 4 modules are in series, I can say it as a 4S configuration. Okay. Therefore, I gave the name as 4S. So the first part, the first column shows the Grewolf optimization. In the middle part, you can see at 0.1 second, as I said, the insulin is changing from 0.4 to 0.8, it is changing. Okay. Similarly, the second column shows if I compared with the improved particle swarm optimization, what's the response. And the third is I implemented the water band object, is the most conventional one, which works best in case of the uniform insulation levels. So you can see a lots of oscillations, okay, and it gets confused. Once it tracks a pit, it oscillates over there. That is the demerit of the conventional MPPTs like water band object and the incremental conductance. So the top row is the power, second row is the voltage, and third is the current. And this is the observation part. So each pattern is hold for 0.1 seconds and it's immediately changed to another 0.1. When first half of 0.1 is, the second panel is 400 watt per meter square. Immediately when it reaches 0.1, it changes to 0.8, which results in such change in the peaks. And this is the comparison table. Okay, you can see. So first we obtained, when it has 400 watt per meter square, we obtained 320 watts. Then when the insolation changes, it became 330. In such scenarios, what I have done, you can see the percentage tracking efficiency, in which you can see the GWO is having better performance as compared to IPSO. And water band object fully fails. So it gets confused and oscillates over the local peak. So 54.54 is the local peak for the pattern 2 and 31.30 is the local peak for the pattern 1. So same thing, I brought a parallel systems to check the efficacy of the same proposed algorithm. So you can see the same system, what happens. So what I did, so the first module, it was 0.5 kilowatt per meter square for first 0.1 second, then it changed to 0.6 kilowatt per meter square. Then this is 0.5 kilowatt per meter square, I made it reduced. Okay, so increment and decrement both are incorporated in this system to check the efficacy. In the first case, only there was increment, but here I incorporated both the increment and the decrement. So you can see these are the peaks for the pattern 3 and pattern 4, and these are the global peaks. Same way, the systems, okay, you can see the same power, voltage, current, and so the first one column is the GWO, second one is the improved IPSO, and third is the conventional water band object, which have lots of oscillations. Then coming to the comparison part, and you can clearly see that in such system also the GWO is giving better performance and is able to track maximum possible power as compared to the conventional MPPT tracking techniques. And this is the formula used for the calculation for the tracking efficiency. So you can see, so this will give a clear-cut idea about the literature survey, which MPPT, how it performs, depending upon the tracking speed, transient power fluctuation, tracking accuracy, convergence, number of tuning parameters, steady state oscillations, efficiency, complexity, and dynamic response. So you can see among this, the proposed one is ruling over the conventional ones, P&O, IPSO, okay, and other two references 20 and 30. One is, I think, flashing firefly, another is the normal PSO. Okay, so these are the comparison in which we can see the proposed is having higher tracking speed, less power fluctuation, highly accurate. It converges to GP, less tuning parameters, zero state oscillations, efficiency high, complexity medium, and dynamic response is good. And these are the experimental results. So in this also I created different patterns. Okay, so pattern 5, pattern 6. Okay, and these are the experimental results which are obtained from the hardware setup which I discussed in the first part. So two different configurations I have taken and it has been validated by using the experimental setup. So what I say that, so this is a part of a decentralized microgrid. Okay, you can take this as a challenge for the DC-DC. If you have a solar photovoltaics, if you have battery, you can connect a buck boost converter. You can take care of this, and you have to also take care of the current fluctuations. So for that you can work in the droop control side. Okay, so overall this is the booming area, and this can be applied in case of electric vehicles. Okay, so overall summary I will give. So you can have a solar photovoltaics, you can have batteries, you can have fuel cells. Okay, you can connect it to DC-DC converters. In according to your use, you can take buck or boost or buck boost. You can connect it to an inverter. It can connect to a multi-level inverter. You can work on the thermal side. Okay, you can replace inductors with capacitors for the DC-DC converters. You can work on the current balancing on the droop control side. So numerous aspects are there which forms the decentralized control. So this is my research part. I work on decentralized control. Okay, if you work on centralized, you need to have a look over many more parameters, which is very complex. So decentralized control is the most, but I think in this area we have a lot of scope, and it can be applied to many things. Like normally we also work in electric vehicles. It can be as an application to electric vehicles. So with this, I conclude my session. So thank you all for your patience hearing. If you have any queries, please you can ask. I will be glad enough to clarify your doubts. Thank you.
Thank you, Dr. Satyajit Mohanty. It was very neat, neat work and some important results we have got from you.
Thank you very much.
I request the participants to interact with the expert. If you have any questions or comments, you can share now, please. Sir, I have two doubts.
Okay.
Yeah, since the speakers are from different backgrounds, uh, can you tell me what is opacity?
Pardon, what is?
Opacity. So you said some glasses and
Okay, that is opaque. Actually, in glass, we say transparent and opaque.
okay,
So
yeah.
opaque means which is not clear, we say it as opaque. So different glasses I used. So these glasses are calculated value. I am not saying it is of that this glass is 1,000, this is 800. It has been exposed to practical. We have a small setup. We have two bulbs. Okay. We have solar cells in between. In between we have rack. Okay. We put these glasses and measure it insulation levels. We have a small setup at IIT Bombay. In that I have worked. Okay, in that we measure the insulation levels. So max it can go up to 1,000 watt per meter square. This is the standard test conditions, and 25 degrees Celsius. Sir, am I clear?
Yeah. Sorry, I just muted. Sorry.
Okay.
Yeah, in the surface of the panel, because of impurities, we can experience some degradation, sir. That is PID. So,
Yes.
yeah, that kind of studies have you performed?
No. I studied on the electrical part.
Okay, not stress and that.
No. Not cell part. I didn't work.
Okay.
Okay.
So, from the cell and conversion side, you are in that.
Yes.
Okay.
And the converter part was the main part
Fine,
of the
fine.
science.
This is from my side. Thank you.
Thank you.
Yeah, please, participants, you can free to ask question to expert speaker.
I think the participants are from different domains.
Yeah.
Maybe it may match or not, because I know Thiru and Shivam both there's little bit work in my area. Shivam is full of my area.
Okay.
Hello, sir. Actually,
Yes,
am
good
I
evening,
audible?
sir. This is
Good
Chandra.
evening.
Sir, it's a very clear presentation, sir. Of course, we are from different domains, sir. And being,
Yes, sir.
let me have a one question, sir, regarding converter side. Will you please give a kind suggestion over that brief converter side, more details about the converter side, sir? Because of what you're saying is correct. Only we are from the different domain, so. But we can understand what you have told is very clear, and it's
Yes.
it's a very nice presentation, and we can come to a conclusion that it's a very nice one, sir. But regarding converter side, could you please give some brief description about the
Okay.
converter side, sir?
Okay. Surely, ma'am.
Thank you, sir.
Surely.
Thank you, sir.
I try to focus more on the experimental part instead of the mathematical part. So experiments should be done because they work on converter sides. Experiments, they give the real output. Okay. So coming to the converter parts, DC-DC converters, it's of two types, isolated and non-isolated. Okay. I worked on the non-isolated part, that is the buck converter, boost converter, buck boost, sepic, cock. Okay. So I worked on all these converters. Among this, the converter which I have chosen, because I had high power applications, okay, high power side, so I have chosen the boost converter. In boost converter, only two things we have: one is inductor and the capacitors. Okay, if you want to work more on that part, you can think of replacing inductors with capacitors, because inductors are of high size, it's bulkier. Okay, in order to reduce it, you need to have a capacitor switch. So that is the one part of the research which is going on now.
Yes, sir. Yes, sir. In starting itself, you have told for low power what we are using the buck converter, and for
Buck
the high
converter.
power we used buck boost, and for the
Like you
charging
can, yes, you can think of a
charging.
step down transformer. Step down transformer in AC, that is same as the buck in DC,
Yes,
and
sir. Yes,
boost
sir.
is equivalent to step up.
Okay, sir. Thank you so much, sir. Thank you.
Welcome, ma'am.
Hello, am I audible, sir?
Yes, clearly audible. Tell.
Yes, sir. Actually, as you have worked on the MPPT,
It's not audible. If you can type your queries, Thiru sir can read the query and ask me. It would be much better.
Mr. Raval, your audio is breaking. Couldn't hear what you say. In alternatively, you can type in chat also. Raval, are you there? His network has issues.
Okay, fine. If he sends some question, you can send it to me. I will reply it, sir.
Yeah, sure.
Okay.
In otherwise, you can share your email ID. So they will
Sure.
they can. Yeah.
Sure.
Sir, I want to ask one question.
Yes, ma'am.
Nasreen Mansoori.
Yes, ma'am.
Sir, I am working on DC Microgrid. So, for connecting, I had done the experiment with portable observer, incremental conduction, and fuzzy logic. So, for my project, which one will be good? Fuzzy logic or portable and observer?
Actually, what is your system, madam? In system,
Sir,
what do
it
you
is
work
a
with?
whole DC microgrid connected
Okay.
for a low voltage right through.
For you can see in current scenario, the things which we discussed, it has actually, for the time, it has been saturated. I will suggest if you work in machine learning, there are 8 to 10 data sets of machine learning, and which is freely available. You can download a software, Orange. The name is Orange, in which different AI techniques are implanted. In that, you can update your data sets, okay, and you will get the best value. It will be much better than this fuzzy portable and observe incremental open circuit. You can have a look over it if you want to do some machine learning techniques.
Okay. Thank you, sir.
Yeah. Any other comments or questions, please?
Sir, this is from Emmanuel School of Mechanical.
Yes, sir. Good afternoon, sir.
Yeah, okay, okay. So this focus is entirely different from our focus.
Yes, sir.
Actually, the cell efficiency is a function of temperature also, but you took only the standard temperature, 25 degree. But in real case, as the temperature rises, for example, in Vellore, say in summer 45 degree or 40 degree,
Yes,
so
yes,
the
yes.
efficiency would come down. So
Yes, sir.
in
Yes,
that
sir.
case, proper cooling is. So did you incorporate such kind of effects in the tracking conditions?
Yes, I will come to you, sir. Yes, sir. Sir, what happens when we simulate something using any software like MATLAB? Okay, we need to have a standard. Okay, so the standard is 1000 watt per meter square and 25 degrees Celsius. Okay, what I did under, if that temperature is set 40 degree, 45 degree, it happens, but it has a, you can say, 0.001% impact on the panel performance.
Okay.
So therefore, I ignored that part. No one incorporates. You can see any research work, nobody incorporates, because temperature has the least effect on the panels. But if there is a change in the insulation patterns, it has a greater impact as compared to the temperature. So that's why I ignored that part.
Okay. 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 Thank you.
Thank you.
Sir, another question, sir.
Yes,
Sir,
ma'am.
sir, for DC microgrid power management, which type of boost converter will you suggest so that we can maintain the DC bus voltage, sir?
For maintaining DC bus voltage, madam, normal boost converter is enough. You need to maintain only 48 volts. For DC
Oh.
microgrid, for DC bus, for we worked in that. DC boost converter is promising in that case.
Okay, sir. Okay, okay. Thank you, sir.
Yeah, so we still have 8 more minutes for questions. If anybody like to rise. Sorry. If there is any question from audience, like to conclude. Thanks, sir, for such a nice presentation. It is like
Thank you very much, Thiru sir. Thiru sir,
sorry. Yeah, please open the video. We can take a
sure,
screenshot.
sure.
So my screen is visible.
Yes, it's clearly visible, sir.
Yes. So I would like to thank our speaker for the third session of the day. Thank you, sir, for delivering such a nice session. And please accept a virtual token of appreciation from our end. Thank you so much for accepting our invitation to deliver a lecture in a very short span of time. So I would also like to thank the coordinator and my colleague, Dr. Thiru Murugan, sir, and for being here the whole day in the FDP program, and so this ends our day one, and we will again meet on tomorrow, that is day two, and tomorrow again we will meet at the first session will start from 10:15 a.m. and yeah, so tomorrow again there will be 3 sessions, and I've already shared uh, uh, the pattern or the schedule of various speakers in the email. So thank you so much for coming here, Dr. Thiruburgan, sir.
Yeah.
Yeah, yes, sir.
Yeah.
Have you taken the pick?
Yeah, I have taken.
Okay. So
Thank you,
Thank
Shivam.
you all.
Thank you,
Thank you
Thiru
all.
sir.
Thank you
Thank
all.
you.
We'll meet
Bye,
tomorrow.
Sure.
Sure.
Thank you so
Okay.
much. Thank you all.
All participants can leave now.